computer. Okay, we're all good. All right, so most of you are familiar with vector operation. I will go over dot product and cross product just to remind you and let you know we are going to use them a lot. All right. I would say until we get to dynamic, we are going to use vector algebra and basic cross product and dot product, and you're required to do them by hand. All right. So you can always check your answers with calculator or computer MATLAB just to make this multiply, but you should be able to do them by hand. Okay. Now, assume for your vectors, your vector P and Q are part of Rn. Now here in our course, N is either 2 or 3. So if you're in the planar or spatial, 2D or 3D. All right. Now, what is inner product? What's the physical sense of inner product of two vectors? Anybody? Yes, Oscar. Projected, that's the keyword. So it's the projection, right? So A dot product B is the projection of A along B, and it's also the vice versa is fine, right? We can denote dot product as P and Q into, I don't know, how do you call this? How do you read this? Huh? I can't hear you. Oh, angle bracket, yeah. A lot of times you won't do that. You do this, P dot Q. That's acceptable. That's probably what I would do, right? And it's P transpose Q. And this is a scalar. What does it mean? So A dot P is a scalar. What does it mean? It's just a number. It doesn't have a direction, right? So it is important to pay attention to what you will get. So it should, everything should make sense. All the calculation you do should make sense to you. So your answer should be expected. And we will see today how you get an answer, but it doesn't make sense. So you have to do like what happens. All right. Now, the norm of vector P is denoted as N2, I don't know, like I just say length of P. And the angle is cosine of theta is dot product divided by length of each. So these are just reviews, right? Just you all know. So let's say P and Q is P transpose Q if P was P1, P2, P2, P3, and Q was Q1, Q2, Q3. If you were going to write that dot product, would be P1, P2, P3, P1, P2. Please turn your phone, put on silent. Oh, Q, sorry. Why is this important to know? Because you're going to be using this to perform this operation by hand. All right, to be very comfortable doing this. So P1, Q1 plus P2, Q2 plus P3, Q3. Now we also know the angle between the two. So basically, PQ is also length of P, length of Q, cosine of theta. This is the projection, right? Of one vector on the other. So now, what is your theta is 90 degrees, pi over 2. What's the inner product of those two vectors? 0. If pi is 90 degrees, so if theta is 90 degrees, meaning that if your P and Q are orthogonal, their inner product is 0. There's no projection. Well, projection is 0, right? So now I want you to pause and think about, and bring my prop, cool prop. I had to go to Michael's to buy these things for the site today. I'll bring stuff for you because you need one of these. when you're solving the problem. What are the angles between your axes? 90. Dot product of each of these axes are 0. I want you, when we get to cross product, also think about this. All right? Yes. What happens? Just the and cosine is a negative number, right? So it means that you're under the other direction. Because dot product doesn't have a direction. Yeah, it's just a projection. Since we don't have a direction, it just gives us a number. Okay. All right. So dot product, everybody comfortable, how to do it, and you know the physical meaning of dot product, right? Now, what's the physical meaning of cross product? Someone else from that area? Matt, what's the physical meaning of cross product? You can cheat and read there. Yeah, you're Matt, right? Yeah, yeah. Are you also Matt? Matt Bishop, raise your hand. Okay, next to you, are you also Matt? Okay, Tyler, all right, so you're the only Matt? Okay, you just don't know. Okay, fine. Tyler, do you know? Okay, who knows? Okay, fine. So the magnet, so there's a magnitude and there's a direction, right? What's the magnitude? How do you find the magnitude? So if you're thinking about the physical meaning, everybody knows the equations, right? We're trying to find the equation. Okay, so that's the direction. So when you have cross product of two vectors, first, the solution is also vector. So that's the main difference with dot product. It has a direction. So you say that the direction is perpendicular to what? Someone was trying to answer for me that. Yes, so the parallelogram, this area, so this is the magnitude and this is the direction. So that's how we get the direction. Now, you see a hand there, so you know you all know right hand. So if this was your x-axis and this is your z-axis, so x-axis and y-axis, or A and B, whatever you want to call it. If you go from x to y, the direction that you close your hand and wherever the thumb points, that's the direction of A cross B. So this is A, this is B, you're crossing. This is the direction of the cross product, right? Now, for the magnitude, you say length of A, length of B, right? Sine of theta. We usually end up here and write that, but we don't really show the direction usually on the paper when you're using those. In this course, you're gonna always think about the vector that points the direction of our z-axis or A cross B, the axis of the result. Now think about this. That's why I keep calling z-axis. If this is your x-axis, this is your y-axis. If you close x to y, which way your direction of your z-axis? Going up. So imagine you have a joint that is rotating this way, right? Now, if it rotates this way, what's the axis of rotation? Is rotating from, imagine that it starts from x, is rotating to go to position of y. What is the rotation axis? Your z direction. That's why when we are solving robotic, like kinematic, we only need to know the axis, the axis of rotation. The other two will kind of, you say not, so I'm going to go down. So this is x going to y, and then z axis will be going down. And it could even be in this direction. It doesn't matter. Any direction, because these are orthogonal. A cross B, always the product will be perpendicular to this plane that they create. All right. So I want you to get comfortable with that. One side is remember how to calculate it. Okay, so we can do that. The other problem is that be able to recognize what's the direction of that vector. Okay, there are two things. Now, you can always have this in your cheat sheet. It's okay, you will have to. I'm going to also teach you another way to calculate that if you forgot how this A would work. But the direction is something that you need to understand. All right. Now, there are some properties. They're not commutative. It's not commutative. So A cross B is negative B cross A. Simply because if you cause Y to B, then your Z axis is going to be the other direction. That's the only difference. The magnitude is the same. So it kind of follows, if you follow the right-hand rule, you already know all of these. And A cross A is 0. The angle theta is 0, right? The cross product of every vector by itself is going to be 0 because they make 0 angle, right? So so I'm going to draw that y-axis because we're going to use that a lot. So if this is x, this is y, this is going to be your z-axis. And they are orthogonal. So x cross product y is going to be z. Now, feel free to do y cross product z and see what's the answer. Try to play with all three of them. You should be able to get the direction correctly. Because since there are three of them and they're all 90 degrees, if you say y cross product of z, you are, well, this is in the space, right? So it will be in the direction of x, right? That's why you need this guy to be able to do in the space. I'll bring stuff next on Wednesday for you if anybody wants. But you can also use toothpick and put in some. So you can always have it if you can remember, or you can just use your 3 fingers. We will use these especially when we are creating the rotation matrix. All right. Again, you just need to practice multiplying them if you want to multiply matrices, well, cross product or dot product. Now, there is another way to do cross product. Before that, I think I asked if anybody knows symmetric, and you guys said no. So, a matrix S in R3 times 3, like in 3D or 3D space, is said to be SQ symmetric, so not quite symmetric, if matrix S transpose is equal to negative S. So if S transpose was equal to S, it would be symmetric. Now, if it's negative S, it is skew symmetric, not quite symmetric. The properties are that S transpose plus S is 0, and the determinant of S is going to be 0. Now, I will tell you how do we use this, but I want you to look at these 4 matrices and tell me which one of these are skew symmetric. We're going to use those properties. So maybe spend a minute or two to identify which one is skew symmetric. Usually write down to be able to tell me. Guys, I'm going to walk around and see what you're doing, and then I'll just solve it myself. How do you know if this is You know, I already posted the annotated versions. You could have seen it, but I wanted to do it. You know, don't be smart. I know what I did. I think this is control me for sleep. Okay, how about this one? Okay. Oh, okay, good. I think we can look at as transposable middle. All right, so what we're gonna do is find the S transpose or the transpose of the matrix and see how it looks like, right? If it is negative of the matrix, then it is symmetric. Again, if you see a symmetric matrix, it doesn't mean it can be symmetric. It has to be the negative of the matrix, right? So here, A, you have 1. Here is -2, 2, 1, right? This looks like negative, but if you go to the next property, you add them together, this is not going to be 0, right? Well, actually, it's going to be 0, right? No, it's not. It's going to be, if you add them, it's going to be 2, 0, 0, 6. So this is not, right? So we find the S transpose. This is S. We know from the properties these two have to be 0, correct? Now let's see this one. S transpose is going to be, well, this is all 0. So -2, -5, 2, 5, 4, -4. If you add these two, this is going to be 0. Right? So from the look of it, let's do one more. Let's do this one. So I'm going to add, let's say, S, this transpose. So this is 0. Transpose here, 1, 2, 1, 2. Then 1, 2, 0, -1, -1, 0. So this is symmetric. So this is not going to be 0. Right? So you guys find B, is this symmetric or is this symmetric? SQ symmetric. All right, this one is also. So these two are SQ symmetric, A and D are not. So these are the properties. So if S transpose is -S, then then you have SQ symmetric. You don't have to find the determinant. That's the properties of. So the determinant of this side. This is just a test to find out. You'll find that for a skew symmetric matrix, there is a formula, like the setup. All the elements on the diagonal are 0. And then the element of off diagonal, they have this relationship. Now, where does A1, A2, A3 comes? So if for any vector that has the, for here, we're in 3D, right? In 3 dimensions. So A1, A2, A3, the way to form a skew symmetric is to place those elements in your 3x3 matrix as such that Aij is negative Aj and Aii is 0. So all the diagonal elements are 0. Off diagonal elements, they are equal in magnitude, but they have a negative. So they are Aij is negative Aji. That's how you create. So Why is this important? Why this is useful? In robotics, a lot of time, instead of doing the cross product of A cross product B, we use an equation to perform the cross product for us. So A cross product B is SQ symmetric matrix of A dot product of B. So we convert cross product to dot product. This is useful when we are trying to find the velocity of our mechanism, and then we have to find the derivative of rotation matrix, and then we have to perform some cross products there. Instead of doing cross product, we convert it to dot product, which is easier computation and easier to perform. So this is why I mentioned it here, because it is connected to cross product, but you'll see the application once we get to velocity kinetics. All right. If you want to see an example how it's done, you can do this. So try to find A cross product B, but don't follow the formula you know from before. Use a systematic to see if you can find it. So does my question make sense? So you have A and B matrix. I want you to find A cross product B, but use the equation I just introduced to you. Find a systematic of A, then dot product of B, or like multiply by B. What is your question? Okay, can we do this one for now? We can go back to that after class. Okay. So did you find this one? Okay. Raise your hand if you finish this. I can go check. Don't look at the annotated version. This is a good practice to see how comfortable you are doing the, matrix multiplication by hand. If it's something that you can work on, just a couple of examples. Be comfortable. So I know these are going to be 0, right? So what's the answer? I know what is that. That's the part I want you to be comfortable quickly doing. Did you do that? About so you could either have a matrix and look at this matrix. You can also create a systematic representation of a vector 3 by 1, which is a 3 by 3. You're trying to do that. So you have a vector 3 by 1, right? You're going to write the systematic representation of it, and then you can use that to find the solution of A cross B, A cross product of B. So now you know this one from the previous slide. Where do you get A1, A2, A3, A1, A2, A3? So you should, so the reason I post the blank version of every lecture you have them, so I don't have to stay on the slide that we are in class. You can always go back. So when you come to the class, be prepared. Don't come and sit down and chill. All right? Bring a piece of paper or have your iPad. If you're using your phone, it's fine. Just follow the lecture and then have a paper that you can solve things. As you see, we are going to do things by hand here. All right? So this is the A matrix. And I created this matrix. Multiplied by B is going to give me -4, -4, 5. You should be able to do this, right? This is going to give this one, and then the rest. All right, you should have the annotation version. In the annotated version, I also added a way of, like a quick way of finding out if a matrix is pure or not. That's just for more exploration. It's not, I'm not going to give you matrices in exam like, hey, if it is a symmetric or not. Okay, this is just a knowledge that you're going to use later, just to show you how you can create one. You can always go back to this formula and use it. All right, so I'm going to close this lecture. So this was what we had to do on Friday. I'll give you like a minute to go to the new lecture. So the blank version is posted, degree of freedom. And hopefully things will make more sense on where we left off last week about it. Anything on Discord? No? Okay. So if Fred is not here, Parth is checking Discord. So if you have a question, you don't want to raise your hand, you can always type there and I'll check with him. All right. How good everybody is on today's lecture? Oh, this is today's lecture. So hopefully we can speed up the pace a little bit because there are a lot of interesting things coming our way. The first thing we want to work on, and again, this is just a knowledge that you need to have when you see a mechanism. You are not going to be finding degree of freedom on a daily basis for a robotic system mechanism. But if you're designing something, you might need to think about degree of freedom. All right. But for that reason, you will have some examples here. I'll give you a formula. You will see it on your homework one. You might see it on your exam one, but it's not going to be part of continuous, like a big project that you're going to solve. So if you are interested in industrial robotics, this is something, if you're going to design a robot that is being used in a factory, this is something you need to think about. All right. Now, we talked about degree of freedom in general. So, an object is really how many degree of freedom it has total. One object in 3D space, suspended 6. One object in 2D, how many maximum degree of freedom you can have? One object. 3, right? So these are our basics, our default. Now, if we add constraints, we are limiting their degree of freedom. Now, if you have 2 objects in a mechanism in a system, then the degree of freedom is going to be complementing each other. It's not necessarily adding. All right, so you might see more than 6 degrees of freedom. And it's because that system has, that mechanism has multiple degree of freedom. Now, how they are related. Before we get to the formula, the kind of joints you will see are these six joints. You have seen revolute and prismatic in the first week. We also have helical. So how does the helical work? So so let's say this link is fixed. Then you have a worm here, for example, and your other link is rotating on the threads of this worm gear, but the direction of motion is on a straight line, but your object is also rotating. But the revolution, so if you had a mechanism that something was here, there will be some changing angle, but the goal of worm gear is to move in longitudinal direction. So the pitch of that gear will tell you how far you have moved. So this joint exists in 3D space, but it has one-dimensional motion, right? If you haven't seen worm gear or haven't used it, just Google how it works. There's just plenty of videos or pictures to visualize it. Then we have cylindrical. The cylindrical joints, it will go up and down and also rotate. So cylindrical joint, which we will show with C, is kind of a mix between prismatic and revolute. You can also show it with PR. Now, how many degree of freedom do you think that has? 2 is rotating individually, and also it can go up and down or whatever direction along the axis. There is universal joint, which show with U usually, and is a mix of 2 revolute, meaning that it will rotate around 2 axes. All right. The third one is a spherical, like your shoulder. How many degrees of freedom? 3. So spherical is 3R. Universal is 2R. If this was a revolute joint. So remember that we had questions about spherical joints. How do we model them? We model them as 3R. So we can put 3R right on top of each other on each axis of rotation, and that's how you model a spherical joint. Prismatic P and helical is just I'm going to show with H. So what are the degree of freedom of each of these guys? 1. So we already saw that 1. So DOF 1, DOF 1, DOF 1, DOF 2, DOF 2. What's the DOF here? 3. All right. So these are the joints that you'll see now. Yes. Oh, okay. So our mechanism will be combination of these joints plus links, because every joint has to connect to links, right? That's how you will see the mechanism. So this is a more detailed table. Basically, same joints here, degree of freedom, and then now there are 2 columns. Column 1 says constraint between 2 planar rigid bodies. Only the first 2 have numbers in them. The other 4 says not applicable. What does that mean? Why? The first 2 are revolute and prismatic. They could happen in planar, in 2D, right? So we can define a constraint for them. The other 4 are only in 3D. So it doesn't make sense to define anything for 2D constraint for them. So whenever you have these 4 joints, you are automatically in 3D or spatial. All right, this is important because you get to define or to determine the number of your freedom, but then you need to know which one are you in M2 or M3. All right. So number of constraint means that. So if you say 6 is the default for special, 6 minus 5 is 1, 6 minus 5 is 1, and such, right? Question? Do you have any questions? Not you. Okay. Oh, yeah. Okay. Thank you. So let me go over the formula and then take a 10-minute with this. Now, there is this fantastic formula to use to find degree of freedom, because sometimes it goes above our head. It's too many things to imagine, so we can just use the Gabler formula. You're going to use this for your programming assignment as well. So your programming assignment is not difficult. You already have the formula. It's more working on the requirement and what I want from how you code. So I'm going to see everyone's coding style. It's a good set to know where everybody is. So the degree of freedom is sum of degree of the bodies, however many bodies, minus the number of independent constraints. So okay, 6 minus 5 is going to be 1. But if we have multi-body, then it might not be easy to follow that. So we're going to follow this formula. So the degree of freedom is M, number of freedom of a rigid body. Either M is 3 or 6. Either you're planar or spatial. Times N, number of links. We're going to count how many links is there. Minus 1, that 1 is always fixed. Minus J, J is the number of joints you really count. Plus sigma Fi. Fi is number of degree of freedom provided by that joint. So that's where the joint becomes important. If it's a revolution, if it's a symmetrical joint, if it's a spherical joint, the number of freedom changes. And what are those? These are, this is that F. So we basically take this number, plug it in that equation, and then we find the degree of freedom for a system. So what I want you to do is write this formula here. So when you solve the equation, you have the formula, and then you can take the, I can take attendance after this. So just bring this equation over there. So for a while, you want to have this equation handy. All right. I'm gonna pause. Okay, so this mechanism that you'll see here, why am I there? Okay. Notice wants to see 3 of me. So this is called open chain mechanism. If you look at this, you have a ground, then you have some joints, some links connected. The other side of your mechanism is open, right? Like human body. My hands are open. So human body is open chain mechanism. It is important to recognize what is open chain and then we see closed chain. Now let's find the degree of freedom for this. We start from here. Ground always counts as a link, but we only count 1 time. So this is link 1. This is another link. 2, 3, 4, 5. So a joint connects 2 links, right? So, and what is M here? M is either 3 or 6. Which one is it? 3, because you're fine. N is number of links. 1, 2, 3, 4, 5. How many joints do we have? So 1 or, that's what I like to do. Identify them because you'll see different joints. So I like to say 4R, so not 4 joints. So I usually put the type in parentheses just for myself. Now, so far so good. Sigma Fi means that adding the degree of freedom that every joint provides for you. So I have 4. What is the number of degree of freedom provided by a revolute joint? 1. So it's 4 times 1, 4. The degree of freedom is 3 times 5 minus 1 minus 4 plus 4. What's this number? 4. All right. So question for you. What if you have a mechanism that looks like this? Had 1 extra joint in length. What's the degree of freedom? 5. Let's just spend some time for everyone to find like alive. Yes. How do I know which one? question? Okay, so sigma fi from 1 to, go from 0, if there's no join, but from 1 usually, to the number of joins. Every degree of freedom that the joins provides. So here basically is 1 plus 1 plus 1 plus 1, because every of these revolute joins provide 1 degree of freedom. So you can say 4 times 1 because they're all 1. All right. Now, for here, M is still 3, N. So ground is 1, 2, 3, 4, 5, 6. Right? So this is 6. And number of joints you have now are 5. So sigma Fi is 5 times 1, 5. If you use the equation, DOF is going to be 5. Oh, sorry, 6. No, 5. No, I will tell you why 5. I know that. These open chain mechanisms are called NR. For all NR mechanisms, open chain mechanisms, degree of freedom is N. So if there were 10 of the revolute joints that connects 11 links, your degree of freedom is going to be 10. So if it is open chain mechanism is NR, a quick way is, so for NR, DOF going to be N. It has to be open chain though. Open chain mechanism. All right. Good. So if you think you're comfortable with this, go to the next slide. That's the conversation. Find out the number, the degree of freedom, and then post your solution to Carmen. It has to be PDF file you upload. If you are using your iPad, is easy to convert to PDF. If you are using a paper, take a photo, convert to PDF using one of the software that you have. I think I usually use what's the software I use? Scanner. So you can use that. So grab this equation and then go to this slide. Yes. What? Yes. So you only count ground as one. Good question. So this is a closed chain mechanism. Both sides are connected to ground, but you only count them as one. All right. Don't just post a final solution. I need to see the procedure. What did you do? Yeah. No, just the ground is one. Yeah, connect them and then that's the one. Yes. Depends on what kind of joint we have. Here is revolute, it's only one, but you can have different joints, right? Since you are in 2D, you only can have prismatic and revolute only, but you will get to 3D. If you have the book, which you all have the link, you'll see plenty of examples in the book, and there are some 3D examples. 3-dimensional. I'll give everybody a few minutes to think about this or work on this. You have until midnight tonight to submit. I'll go on the next example after this. It would be that I want you to spend some time to solve it. Yeah, screenshot, yeah, it works. As long as it's PDF, because if it is photo, it would sometimes comes like gigantic on my iPad. I'm like, no, I'm not ready. Yes. So when you submit to Carmen, it goes under your name. So it's not, yeah, if you go to module, that CP3 is the same question and you can upload. This is basically to kind of go over how things work in the past. And if you haven't used me before. Oh, okay. Yeah, you can go, but how long does an continue? Okay. Can you tell them you'll be late a little bit? Okay, good. Yeah, tell them because you see that most of the examples. Yeah. All right. So hopefully you've done this. If not, continue working on. I'm gonna solve something similar, but a bit with more links and joins. So you should be able to check your work. Did you have a question for me? Do it, Mike. Okay, I'll extend it to midnight. I'm gonna post the solution shortly, but yeah, I'm gonna extend that to midnight. All right, so for this one, what is M3? This is a cold chain mechanism. So the whole ground here, I'm gonna do this just to show you this one ground. So ground is going to be link 1, 2, 3, 4, 5. So N is going to be 5, and then R, 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 R. So you have to look if this is a joint or it's just a valve that does not move. Here's a joint. This shows the circle. So 1, 2, 3, 4, 5. J is 5. Sigma Fi is going to be also 5 times 1, which is 5. So this is 5R. DOF is going to be 3 times 5 minus 1 minus 5 plus 5. DOF is 2. So if you look, if you want to like kind of imagine how it works, if you push one of this link, go probably here, and then this, if you also push this one, for example, these two kind of work together, then the third one, even if it's a joint, is not going to move independently. Yes. What is it? I'm going to show you, yes. The formula doesn't fail. Sometimes there's redundancy in the system that you have to be careful with. Yes. So degree of freedom is 2 here. Let's go and see that. That's a good question. Redundant joint. So let's solve for this example. How many degree of freedom? Solve. See what the equation is. Ground is 1. And this is 1 link. This is 5. Okay, there's R, 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 R. J6, sigma Fi. 6 times 1 is 6. So DOF is 3 times 5 minus 1 minus 6 plus 6. What's this? The solution. 0. This obviously moves, right? What's the problem? Raise your hand, don't say it. What's the problem? Huh? Where is the redundancy? I know it's very easy. So get rid of the joint in the middle with the link and everything. Because your system still does the same thing that it would do. So Gaussian formula will fail if you have over-designed redundancy in the system that doesn't add an extra motion. So you have to be careful when you're using the formula. Why someone would design redundancy let's say these are motors, right? Okay, what do you want to say? So, you know, FMEA, so it's failure mode analysis. So what if one of these motors doesn't work? You still want the system to move. So one is the backup. But it's on purpose. It doesn't mean that someone designed this wrong. It might have required to have a backup in the system. So when you're calculating the degree of freedom, did you remember when I said you find a solution on the paper? You have to make sure it makes sense. So here it has to make sense. Now, if you take those lines in the middle and all those join out, then your degree of freedom becomes 1, which makes sense. All right. So in general, what I expect from you is whenever you, whatever you calculate and put on the paper and submit, you have to be able to defend it. If it didn't make sense, it might not make sense. It might be wrong. You know, something might be wrong. Try to investigate what's the reason. Is it the fault is you miss the calculation somewhere, or the system has a fault, or a redundancy on purpose? Make sense? Yes. So you will find the equation, good question, because I have done that before myself. The answer will be 0, and then you say that, oh, it's not possible, something like that. And you explain what you think went wrong, and that's acceptable. So you will see that in some of the examples, you find a solution and something is 0, and obviously it shouldn't be. And I want you to tell me, investigate why. All right? Yeah, I never have multiple, barely have multiple choices, always open questions. All right. So we have two examples. Again, I will post the annotated version. You should be able to follow the annotated version for this example. Both of them are correct, but I will review them at the beginning of Wednesday.